Chapter 5, we're going to start our discussion on probability. Kind of inch our way towards it as we get closer to dealing with methods of sampling, which we talked about in Chapter 4, but didn't actually take any samples, but just looked at the different kinds. So in Chapter 5 here on Section 1, we get into some of the really fundamental stuff about probability. Okay? It measures the chance of an event occurring. Okay? It can always be described as a number between 0 and 1. If you are saying the probability is 0, you're describing an event that cannot happen. If you have an event where the probability is 1, you're saying that it is absolutely certain, or in other words, that it's going to happen. Where it says the law of large numbers, this really comes up. We see this in the process of doing a simulation. If you take this chance process and you repeat it again and again and again, eventually it's going to settle on the probability of the event, like the actual probability of the event. Below, it's showing you a super basic simulation with flipping a coin and the proportion of flips that'll be heads. Right? Now, just some common sense tells you that it's 50-50. But what the law of large numbers is saying is keep flipping it again and again. You can see after 7 flips, it's not on 50-50. 13, 19. It's start here. This line right here is 0.5. So it's starting to settle on it. This one goes all the way up to 500, and you can see that the graph is really starting to settle on 0.5. Okay. That would be like a simulation with 500 trials. If your simulation is good and accurate, after a large number of trials, the probability should be getting really, really close to the actual probability of that event. Again, in this case with the coin, it's getting really close to 0.5. Right on this warranty one, because we could see any kind of variety of just basic probability problems that we should be able to solve. They typically don't require a ton of work. So it tells us that 5% are going to need to be replaced off the warranty. That's 5 out of 100. Simplest terms, it means basically 1 in 20. Right? 1 in 20 isn't going to go as planned. So we could take the $150, and the problem is describing that if we knew which phones were going to go bad, we would just make them pay to replace them, or maybe just don't give them that phone in the first place. But that's not the case. Right? We don't know which, when they're sold, what the 5% is going to be. But if we multiply it by that 5%, or you could think about it like dividing by 20 and splitting that $150 over everybody, right? Just think of it in like groups of 20, right? If we just have everybody chip in $7.50, we'll be covered, and we'll have the money to cover the phones that don't work, that need to be replaced. So it would essentially mean for this phone, and we typically don't want to make any money off of the warranty. We should make more money by making bad phones. In fact, it may not even be legal. I'm not sure. But to cover the expenses of replacing the phones, that's basically what it means, is charge $157.50. You've got the cost of the phone, that's where the $150, that's where you're going to make your money. But tag on the $750, because we factored in the probability of 1 out of 20. And that's realistically what you would charge. Now, if the phone doesn't work for whatever reason, we could say that it's replaced for free, because we know we have the cost to replace it. just kind of a random set of questions, just thinking about probabilities. Just from that list of numbers. If the event is impossible, we'd say its probability is 0, right? And for the second one, right, it's 1. Those are the two we've talked about. This outcome is very unlikely, but it will occur once in a while in a long sequence of trials. I would say 0.01. That would work out that it'll happen about once in every 100 trials. Okay, you could think of this as, because a lot of you may like to think of probability as a percent. That is an event that has like a 1% chance of happening. Okay, every 100 trials, you should see it happen about once. This outcome will occur more often than it won't. Actually, if I go back to the previous one, I left off 0.3. That's going to happen like 3 out of every 10 trials. So it's a little bit unlikely. It will not occur more often than it does, but the second part where it says it will, occur once in a long sequence of trials, it'll basically happen like almost once every 3. And that's not really a long sequence of trials. Will occur more often than it won't. I would put 0.6, and you know what? I'll also put 0.99. Okay, 0.99 will occur a lot more often than it won't. If you were to do 100 trials, you should see it happen about 99 times. But same is true for 0.6. There, I would put both of those. I guess you could technically put 1 there as well, because it's true. It'll happen a lot more than it won't, because it never won't happen. But I left 1 off. I don't think that wording here kind of seems to imply that we're talking about events that at some point will both occur and not occur, but they have probabilities where they will occur more often than they won't. All right, so I really like looking at this one because it illustrates what probabilities are getting at. Okay? Talks about the odds of, I think, U.S. adults eating breakfast, that it's 0.61. Okay? The first part has a good description of what that really means, that if you ask a large sample of adults if they eat breakfast, about 61% will answer yes, they do. Okay? A large sample. Go down to this next question. Why doesn't it mean that if 100 U.S. adults are chosen at random, exactly 61 of them usually eat breakfast? Well, it comes down to this. We'll hit the actual probability if we look at a large sample. Okay, it can be a little bit tricky to put a number on that. Is n equals 100 large? Right? Would this satisfy the law of large numbers? Maybe, maybe not. It's pretty large, so my guess is you'll probably get about 61 that will say yes. No guarantees it'll be exactly 61. But if you're going to stay at that sample size, this is a huge concept as well. If we took multiple samples, we'd actually expect them to vary. I could do one and I get that 57, right? 57 out of 100 said yes. You could do your own sample and you saw that 60. Someone else could get 70, 64. Right? We shouldn't be that far away from 61 unless we get a really, really weird sample of 100. But our law of large numbers doesn't say that we're going to hit our actual probability at a sample size of 100. It just says once you have taken a large sample. Okay, so it should be close, but maybe not exactly. going to use hat theory for this description for a simulation. Same kind of thing that we could use hat theory or a random number generator. Here's what it'd look like. It's kind of like it's like a hat theory, but it's got one extra little element to it. So you write down each of the 10 numbers. On separate pieces of paper and put them in a hat. Randomly select 3 and calculate the sum. That would be like one trial. So repeat this process and record 2 things. This is where it kind of has a little additional piece to just a typical hat theory one that we did in chapter 4, where you're just describing how to take a sample or to design an experiment. Okay? Repeat this process and record the number of times the sum is 18 over the total number of trials. Because that is really what we're after, and that part there is a huge part of describing the simulation. We got to keep track of both of those, because a probability is going to be formed by a ratio. On the top of our fraction, we have all the trials that we did get a sum of 18, and then on the bottom, we're just keeping a tally of here's all the trials that we did. After a large number of trials, this ratio is the estimate for the probability. Okay? First part probably seems pretty familiar. Okay, put them all in a hat, randomly select 3, check and see if they add up to 18. But this last part is usually where things can get a little bit tricky, that you've got to have that. Remember to keep track, and you have to, if it's a simulation to estimate a probability, you have to keep track of these 2 things. On the top of my fraction, I'm saying the event that we're looking for is getting a sum of 18. Keep track of that. Okay? How many times did that happen? But you also, on the bottom of your fraction, keep track of the total number of trials that you did. Okay? Because if I did, 300 trials and I got a sum of 18, 67 times, I have no idea if that's even accurate at all. Your estimate would be 67 over 300. That's what you're trying to keep track of.